Hello, everyone. I'm William, and I'm here to share our experiences in understanding and addressing the scalability issues of RDMA-based container networks. This is a joint work with Tsinghua University, Alibaba Cloud, University of Southern California, and UIUC. Containers have become a pivotal technology in modern computing, and it's changing how we build and deploy applications. For example, they can serve as the foundation for microservice architectures. Containers are now also widely used in large-scale AI workloads. They enable the deployment of massive LLM clusters efficiently. So in the meantime, container networks enable seamless data communications among containers in data centers. It typically supports critical features like multi-tenancy and network virtualization. And most importantly for our discussion, container networks must deliver high performance and low latency communications among the containers. So to achieve this goal, container networks are usually built based on RDMA NICs to offload data traffic and network functions from the host OS to the dedicated hardware. In this way, network traffic can all be processed in the hardware, and the packet switching and the network virtualization can be more efficient. The resulting RDMA-offloaded container network, or RCN for short, is expected to have at least 3 times of performance gain compared to traditional network stack inside the host OS. So despite the performance advantages, an RCN in production has scalability walls. Let's look at a real-world example from Alibaba Cloud infrastructure. A typical RCN cluster has 8,000 physical hosts and 40,000 RDMA NICs, serving around 0.5 million active containers. However, we find that when the network scales from 0.4 million to 0.8 million containers, the aggregated bandwidth over an RNIC can decrease by at most 87%, and the end-to-end latency can spike by 34 times. At first glance, this is easy to understand because the hardware resources in RNICs are limited. But as a cloud service provider, we wonder which components actually are causing the bottleneck and whether we can take active measures to avoid them. To understand these scalability walls, we conducted a year-long measurement study from April 2023 to April 2024, analyzing a large-scale RCN deployment in Alibaba Cloud. And each measured host is equipped 1 to 8 RNICs, and we get RNIC statistics such as the sending and the receiving rates and the number of connections. And we also monitor the open vSwitch and the CNN events, including flow table lookups and subnet allocations. Our study uncovered concrete symptoms of RCN scalability walls, each tied to specific layers of our stack. Among these symptoms, over 80% are related to RNICs. For example, we found offloading flows from containers to RNICs can lead to kernel instabilities when the workload of the RCN is very heavy. In some cases, the kernel can be stagnated, and in other cases, the kernel can even crash on offloading new flows. So as you can see, RNIC hardware is also constantly triggering the scalability issues. We find that when the number of flows increases on RNIC, flows can intermittently go into the software stack, and which incurs significant performance degradation. Here we show the concrete impacts and the monitoring data of these symptoms in the real-world scenarios. When repetitive flow offloading happens, our monitoring system reports that the open vSwitch bears considerable lookup, miss, and loss events. The RNIC seems to refuse to offload these flows and constantly pass it to the software stack for processing. This is reflected in the performance fluctuations in the container communications. Here is the performance of an LLM training cluster when the flows are repetitively offloaded. In the worst case, the throughput is reduced to near zero, and the user can even complain about it. We also summarized the detailed failures per year of the different RNIC models in production. And we noticed that newer RNICs present higher failures per year. This can be attributed to 2 facts. First, newer RNICs have more data to be synchronized. And second, newer RNICs kernel drivers are more complex but not tested enough. Here's another example of the undesired RNIC performance. We noticed that the overall end-to-end latency can increase after a specific flow is offloaded to the RNIC. And even if the workload is reduced to a low level, the performance of the RNIC cannot recover from the past high workload. So given the above unexpected performance of commodity RNICs, as a cloud service provider, we wish to understand why these issues happen and if we can take active measures to fix or avoid them. However, this is not easy for container service providers like us in practice. First, commodity RNICs is a black box. We have very limited visibility into their internal implementations, and their micro behaviors are not recorded in their official data sheets. And second, although we can resort to RNIC vendors for some kinds of help, it's still difficult for them to reproduce our encountered issues since we cannot share real-world workloads to them due to the security and the privacy reasons. While our production workloads still push the RNICs to the extreme. So to address the above dilemma, we present Scalability, an RNIC performance testing and debugging tool for container service providers. Our key idea is to infer the architecture and the performance model of the black box RNICs. Our key insight is that today's RNICs in an RCN provide RDMA verbs and the e-switch interfaces for bypassing solid stack processing so as to efficiently forwarding packets among containers in the same host or across different hosts. In other words, our method uses RNICs common abstractions for performance testing and modeling, and it fundamentally differs from the existing black box testing or white box analysis as we take advantage of our domain knowledge, which is more like a gray box approach. Here is how we conduct testing. We first build different testing dimensions for each RNIC. For RDMA verbs, we configure the different RDMA hardware resources like QPs and CQs. For the e-switch interface, it's actually a bunch of flow tables that work in a match action manner. In fact, this has become the de facto standard in an RCN for packet switching. So as you can see, when an RCN packet goes from the container into the RNIC, it will first be queued and dequeued for buffering, and then the RNIC queries the offloaded flow tables for packet matching, visualization, and forwarding. We then change one input workload dimension, for example, the number of QPs and the number of flow table entries, while controlling the other dimensions unchanged, so as to test which input workload dimension contributes to the possible performance degradations. However, here we face a key challenge that today's RNICs are highly configurable. For example, the NVIDIA Connect X series RNICs has at least 192 bits for packet matching in flow tables, and each of these mask bits can be configured individually. And also, the number of QP, CQ, and WQ combinations further adds to the complexity. So to address these challenges, we propose the combinatorial causal testing. Our key idea is to leverage the input dependencies to filter out the combinations that lead to packet loops or unreachabilities. In this figure, packet A can correctly be delivered to the destinations while packet B goes into forwarding loops, and packet C goes to an unreachable destination. In this way of optimization, we can speed up the testing validity times. Through the above testing, we can refine the critical path of packet processing inside an RNIC by building the causal relationship between the input configuration changes and the actual performance. In particular, we found that for the NVIDIA Connect X series, the number of matching mask queries in flow tables can significantly affect the scalability of the RCN. This is because different matching masks in the flow tables are organized as different flow groups inside the RNIC. When a packet is dequeued, it will sequentially query different flow groups. Such queries increase the packet processing complexity. For example, when the average flow group query is 10, the bandwidth of ConnectX-7 RNIC bears 5 gigabytes per second loss. And when this number increases to 20, the loss increases to 100 gigabytes per second. And in contrast, increasing the number of flow table entries inside a flow group hardly affects the performance. We assume that the flow table entries within the same flow group is organized as RDMA. With Scalability, it's easier to for container services like us to understand the performance impacts of different RNIC components. And apart from the above performance interpretation, we can also explain other performance issues as we have previously reported. For example, we find certain RNIC flow counters are not updated in time, and when the network scales up, this makes the obvious mistakenly believe that the corresponding flow on the data plane has no actual traffic, leading it to delete the flow by mistake and therefore forcing the traffic to go through the software. So from the view of the control plane, the flow hits the software OVS and does need to be re-offloaded. And even worse, we noticed that when we offload more than 7,000 VX line context, the ConnectX-6 RNIC can be unresponsive, and this leads to the kernel driver constantly waiting for its response. And as a result, the kernel stagnates and finally can even crash, which affects all the containers in this host. Besides the interpretations for the unexpected performance and the scalability walls, Scalability also helps us to build a performance model for performance prediction and in production. As we have identified the bottleneck components in flow group queries, we predict the bandwidth and the latency through the statistical fitting over the number of flow group queries. As you can see, we can predict bandwidth of an RNIC using a radial basis function, while the packet processing delay can be predicted using a simple linear function. Scalability helps us to predict when the performance issue is likely to happen so that we can take active measures to mitigate them. With the performance insights from the Scalability, we proactively optimize the performance of our RCN under high workloads. We organize the offloaded flow tables as a multi-level cache to minimize the average flow group query delay. Specifically, we divide the flow groups into hyper and cascading flow groups. The former match all the fields of a packet so that all flows can be recorded in the headmost flow group for the minimal delay. Of course, this can quickly fill up the hyper flow group. So we also set a cascading flow group after the hyper flow group for matching a broader range of packets. In this way, Scalability ensures that most of the packets query around only once in the flow groups. We evaluate Scalability using both middle-end RCN and the real-world workloads. The evaluation shows that Scalability significantly improves the performance by 40% in macro benchmarks and improves the performance by 70% in production given the high dynamics of the production workloads. Although Scalability determines the flow table organization before offloading flows, it incurs negligible side effects on flow startup performance. In summary, in this work, we conduct first study to uncover the scalability walls in a large-scale RCN and pinpoint the culprit to be RNICs. And to address this, we devise combinatorial causal testing based on RNIC common abstractions so as to efficiently approximate the RNICs internals and infer the root causes of the performance issues. And finally, we devise an effective method to accommodate RNICs to RCN scaling. And evaluation on real-world workloads and the feedback from the vendors confirms its efficacy. And finally, this work is specially supported by Feng. And thank you, and I'm ready for Q&A.